Now we move on to implicit differentiation, which is section 3.8. And the point of this section is to provide a technique for finding the derivative of a function when it is only defined in an implicit way. So usually we're used to dealing with functions that are given to us in terms of a formula that depends on x. But sometimes there are relations between y and x that implicitly define a function of x. But the dependence cannot be written down explicitly, so y cannot be solved in terms of x. And in those situations, it is still possible to find the derivative if we are careful and keep in mind that the variable y is a function of x. I mean, you cannot take just any value, and in those because I mean it depends on x in the sense that it has to satisfy a certain relation. So if x is fixed, y needs to be constrained to a finite, in most cases, a finite set of values. So now this technique will also allow us to find derivatives of other kinds of things, which will, I mean, we can find the derivatives directly, but this tool will provide an easier way to derive uh, the formulas for the derivatives of many inverse functions in a cleaner way. Okay, so what do I mean by that? I mean, just to be more explicit, let's start with an example. Uh, Here, let's consider the set of points x comma y, such that y, no, or points x comma y is y times cosine of y plus x squared is equal to x cubed. Now here, y is a function of x. But the question is, can you solve for y in terms of x? So if you take a look at the relationship between x and y, you'll notice if you try to move this, say, to the other side, you'll have y on one side and y also on the other side, because you're divided by cosine of y plus x squared. If you try to take the arc cosine on both sides, you'll still have y to deal with inside the arc cosine, and so the trying to solve for y, it is virtually impossible. So the best bet that you have in this kind of when dealing with these kind of expressions and dealing with these kind of situations is to try to do what we call the implicit differentiation. So use this technique, use implicit differentiation if you want to find the derivative of y in terms of x. And why do we know that this is a function of y is defined implicitly as a function of x? because if you say fix x to take on a particular value, then y cannot just be anything, right? So if x is 0, then y cannot just take on any arbitrary value. I mean, it cannot be 100 or a certain number, says like pi over no, or say it's pi, and cosine of pi will then be equal to -1, and times y, which is equal to pi, will be minus pi. So minus pi will be equal to 0, and that will be a contradiction. So when you fix x, then the values of y, the possible values for y are limited, and that's why you have a function. And locally, near a point that you know belongs to the set of points to satisfy this relation, there's only one value of y that makes this equality true. So what do we do? So what do we do if we're asked to find dy dt at the point P, where P is the point 0.05 pi over 2. So how do we tackle this problem? Well, as I said, we cannot simply write y as y of x is equals to some function of x, because this is not possible. You will not be able to solve for y in terms of x. And so what we're going to be doing here is we're going to take the derivative with respect to x on both sides, and keeping in mind that y is a function of x. So this is what we'll do. Okay, but the derivative here is the derivative with respect to x. So we use the product rule. So it's y prime times cosine of y plus x squared plus y, and then the derivative of cosine y plus x squared. All of that prime is going to be equal to the derivative of x cubed, which is 3x squared. Now, well, y prime is just y prime. Cosine of y plus x squared is just that. Then y, and to compute the derivative of this cosine of y plus x squared, we use what we just learned, namely the chain rule. So we take the derivative of the outside function minus sine of y plus x squared, and we multiply this by the derivative of what's inside, so that, and remember that we're not differentiating with respect to y, so we don't get 1 when we differentiate this, we get y prime. So this becomes y prime plus the derivative of x with respect to x, which is just 1, and then plus 2x. And this is equal to 3 x squared. And again, so remember, that if you take the derivative of y, this is y prime. We are differentiating, we're taking the derivative with respect to x, not y. That's the whole point. I mean, we're assuming that y is some f of x, and we're differentiating everything with respect to x. And now that we've managed to find an expression for the derivative, we simply plug in the values. So we are asked to find the y prime at the point p, which is 0, 5 pi over 2. So that means x has to be set equal to 0, and y equals 5 pi over 2. So y prime times cosine of y prime is not known yet. We just know y and x at the point. This is what we want to find out the value of. So 5 pi over 2, which is y, and then plus 0, plus 0, plus 0, then plus y, again, 5 pi over 2, times minus sine of 5 pi over 2 plus 0 plus 0, times y prime plus 1 plus 0, and all that is equal to 3 times 0 squared, which is 0. Okay, now what is cosine of 5 pi over 2? What is cosine of 5 pi over 2? Well, if you remember the graph of cosine, so this is 0, pi over 2, pi, 3 pi over 2, 2 pi, and 5 pi over 2. So this, at this point, the function cosine vanishes. So this term here is 0. So we just get 5 pi over 2, which comes from this term, well, minus that because of the sine, and then times sine of 5 pi over 2 is just 1. You see the same thing. You look at the graph of the function and you'll realize that the sine of 5 pi over 2 is just 1. And times y prime plus 1. And that's supposed to be equal to what's on the other side, which is 0. Okay, now we can divide by minus 5 pi over 2, both sides, to then get that y prime plus 1 is equal to 0 at that point, at the point P. So this implies then that y prime is equal to minus 1. So this is at point P. And here, well, we didn't do something that you need to do whenever you're working on this kind of problems. You're given a point. First thing to do here is to check that the point actually belongs to the set of curves, or the point satisfies this relation. Otherwise, you're computing something that doesn't make sense, because this doesn't belong to the graph. So for instance, it will be the same as asking you to compute the derivative of the function x squared, where that function takes on the value minus 100. Since that function never takes on the value, they're asking you to do something that doesn't make sense. So here, they're asking you to compute the value of this derivative at a certain point, so that this point better satisfy this relation here, up here. Otherwise, they're asking you to do some nonsense. But this can be easily checked. So when x is equal to 0, the right-hand side is equal to 0. Y is 5 pi over 2, but fortunately, cosine of 5 pi over 2 is 0, so you get 0 times 5 pi over 2, so we get 0 on both sides. And that is exactly what we need. So we're going to go over some more examples, and this is basically what you need to do. I'm just going to try to make sure you get the point across that you need to be, you get the point, I get the point across that you need to be very careful when differentiating things implicitly, because you should not get confused about taking derivatives with respect to y when you're supposed to be taking derivatives with respect to x. Okay, so we're going to be doing more examples, and then we'll move on to some applications, as we said.